Hello everyone and welcome to my talk. In the following, I will present our work efficient AutoML for clustering analysis. This is a joint work with my colleagues Manu Fritz and Holger Schwarz. Clustering analysis is a fundamental primitive in data mining to detect curtain structures in your data. However, when applying clustering analysis on a new dataset, analysts often ask themselves, which algorithm should I use? Since each algorithm may be more suited for a different kind of dataset, and which hyperparameters should be used in combination with the clustering algorithm. This is also dubbed as the combined algorithm selection and hyperparameter optimization problem in the literature. While experienced analysts may be able to select valuable algorithms and hyperparameters efficiently, this is a tremendous challenge for novice analysts due to their missing experience and lack of domain knowledge. Recent work in the area of AutoML is able to address the cache problem efficiently. They are able to address very large configuration spaces by using optimizers that explore them greedily. Here, a configuration consists of an algorithm and its hyperparameter settings. And hence, the configuration space describes the search space of all possible configurations. Yet, the existing AutoML systems solely focus on supervised learning tasks, whereas clustering is an unsupervised learning task. So the question remains how to apply the concepts to clustering. Note that while the previous talk focused on the single execution of a case-center clustering algorithm by trading off runtime and quality, here we focus on the combined selection of clustering algorithms and their hyperparameters. In the following, we will first discuss limitations of related work and subsequently present our novel AutoML for cluster approach. In the evaluation, we unveil the accuracy and runtime of our approach in contrast to existing approaches, and finally conclude this talk. We divided the related work into three different groups. The first, as mentioned before, are the AutoML systems for supervised learning. Here are, for example, AutoWK and AutoScaler. However, they are only focusing on supervised learning tasks. Regarding clustering, there are two different kinds of works. First, the algorithm selection for clustering, which basically uses meta-learning to predict a clustering algorithm for a new unseen dataset. However, they ignore the hyperparameter optimization. The third work overall is the hyperparameter optimization for clustering. This work solely focuses on optimizing the hyperparameters of a single clustering algorithm. Hence, they ignore the algorithm selection, which means there is currently no work that addresses the cache problem for clustering. To address this, we propose our AutoML for cluster approach, which is able to address the cache problem for clustering. Our approach basically consists of three parts: the inputs, an optimizer loop, and to return a best configuration. First, we have three inputs: a dataset, which is intended for unsupervised learning, which means it does not contain any external information like class labels. And because of the missing external information, we use an internal metric which assesses the internal structure of clustering results. Moreover, we require a budget which defines the resources that can be used by the system. In our work, we use as budget the number of optimizer loops that are performed in the second step. Here, multiple loops of a hyperparameter optimization technique are used. So, for example, of base, hyperband, or a combination of them. Each of the optimizer loops consists of three steps. First, a clustering configuration, which is basically a clustering algorithm and its hyperparameter settings, are selected from the configuration space, which contains the possible clustering algorithms and hyperparameters. This is the step where most optimizers differ in how they select a configuration. Yet most of them aim at greedily exploring the configuration space by trading off exploration and exploitation. Exploration here means to explore new regions from the configuration space, while exploitation means to exploit already well-performing regions. In the second step, the selected configuration is executed on the dataset, and the result is evaluated in the third step using the internal metric. These three steps are repeated until the given budget is exhausted, which means until L optimizer loops are performed. If this is the case, we choose the best configuration, which is basically the configuration that achieves the best metric value from all evaluated configurations. The shown concept here remains generic regarding which optimizer is used and which internal metric is used. However, an important question here is which combination of internal metric and optimizer leads to the best results for clustering analysis. An additional challenge here is to determine a suitable value for the budget to achieve valuable results in a short time frame. To analyze these questions, we performed an evaluation on which we will detail in the following. In the evaluation, we used 24 synthetically generated datasets, and since we generate the datasets, we also know the cluster labels, and hence use an external metric, which is the adjusted mutual information, to measure the accuracy. We use 4 optimizers that are often used in the literature, which are random search, Bayes, hyperband, and BOHB. And for each optimizers, we use 3 commonly used metrics, which are Davis-Baldwin, Kalinski, and Silhouette. In total, this means we have 12 different instantiations of AutoML for class. And we compare these 12 instantiations to 3 baselines, which are basically 3 times an exhaustive search with each of the 3 internal metrics. So first, we examine how to choose a valuable budget for our AutoML for class system. To this end, we evaluate how accurate the different instantiations of AutoML for class perform for an increasing budget, while we measure the accuracy after each optimizer loop. Here we show the results for the different AutoML for class instantiations, so for the different optimizers and for the different metrics. We see that at the black vertical line, which is around 60 optimizer loops, the accuracy does not increase significantly. And hence we use this for the following accuracy comparison. Moreover, we observe in general that there are very accurate results with over 90% are possible, and that the Kalinski-Harabash metric, which is the blue line, tends to achieve the best results, while the Silhouette, which is the green line, achieves the worst results. Because of this, we do not include the Silhouette in the following accuracy comparison. Regarding the accuracy comparison, we show the results here. Note that the numbers underneath the boxes show the median results, so for the baselines and for AutoML for class. We observe that the best results of AutoML for class are achieved with Kalinski-Harabash and in the hyperband optimizer. And this only deviates 3% from the best result of an exhaustive search, while it is even better than the exhaustive search with the Kalinski-Harabash metric. Yet, AutoML for class only explores 60 configurations, while the exhaustive search explores the whole configuration space. To make this clear, we investigate in the following how the difference is regarding the runtime. Here, we show the runtime results for AutoML for class and the exhaustive search. Again, note that the numbers here show the median results of the runtime. Also note that the first number show the results for Kalinski-Harabash, then for Davis-Baldwin, and for the Silhouette for each optimizer. We observe that the fastest results of AutoML for class are achieved within 74 seconds, while it took over 21,000 seconds for the exhaustive search. Hence, we achieve speedups of up to 437 times, while being nearly as accurate as the exhaustive search. So to conclude this talk, we presented our AutoML for class approach, which is an AutoML approach for clustering analysis. This approach is efficient as it explores large configuration spaces greedily. It also remains generic regarding optimizer and metric instantiations. However, we showed that the best results are achieved with hyperband and Kalinski-Harabash. We also presented that speedups of up to 437 times, while only deviating 3% in the terms of accuracy from an exhaustive search are possible. So thank you for your attention, and if you have any questions, feel free to ask them.